Hello everyone, thank you for joining me today. My name is Minam and today we're going to be looking at pressure both at a surface and pressure at a depth. So we have a few learning objectives and they are to define pressure, to be able to understand pressure as the force exerted by particles on a unit area, and to be able to understand that pressure at depth is really the pressure exerted by a column of liquid. And we also have a couple of equations to recall that pressure is equal to force over area, and to recall that pressure is equal to HPG, which is a new equation, so let's get right into it. So first what we want to do is actually define what pressure really is. So I have here the definition. Pressure is nothing but the force applied per unit area. So let's have a look at this more intuitively. Like if we have an object, right? So let's just say a normal cube, right? And I have a particle in it. Now, we know that all particles have some type of kinetic energy, which means that they're always vibrating. And if I'm just looking at a single particle here, say a gas particle, this particle is always going to be traveling in all sorts of random directions at lots of different speeds, right? So when it hits the wall of the actual container itself, is it just going to stop there and just like stand still? No, it's going to rebound. Why is it going to rebound? Well, that's because at the wall here, the particle will exert a force, and I use the word exert and applied kind of interchangeably, but they mean the exact same thing. They really mean placed upon, right? So the particle will place a force upon the actual wall of the container itself, and because of Newton's third law, which tells you every force has an equal and opposite reaction force, the box, right, let's just call it a box, will exert an equal and opposite force back on the particle, and so the particle will rebound. But this initial force here, right, that the particle exerted upon the actual box, this is the pressure. Because think about it, right? That particle can only hit one exact tiny space on the actual box itself, right? Enough space for the actual size of the particle itself. If the particle is very large, it will cover a very large space. If it's very small, which it is, it will cover a very small space, but it's still a units of area. So what pressure is nothing but, actually let's do it in green. Pressure is equal to the force, which is always in newtons, over the units area, which is in meters squared. So we end up with units for our pressure equation being newtons per meter squared. But that's a bit of an awkward unit, so we have a much more standard unit, which is Pascal. So that's what we really use when we're talking about pressures, Pascal. And now one common Pascal value you need to know is atmospheric pressure, right? So the pressure you and I are under, just due to the air all around us colliding with us and exerting force on us. So that is 101 kilopascal. So 101,000 pascals is equal to atmospheric pressure, or 1 atm, right? That's another unit for you here, atmospheres. Okay, so that's all about pressure. Now you understand what pressure actually is, its definition, and how it works logically. Now what we really want to understand is pressure at a depth. Okay, so I have here a very common diagram and of apparatus that you often get in schools to really represent how pressure at a depth changes. Okay, so I have here just a big tub of water, right? So I'm going to call this like turquoise stuff water, and you can see here that I have 3 nozzles, right? So these nozzles are really an outlet for the water to flow out of the actual like bath, you could say, right? Don't really know what you would call this container, but okay. Now what's really interesting is that the shape of the water jets that come out of the nozzle themselves. So we can see that the nozzle right at the top is the weakest jet. So this is the weakest. So weakest really meaning that it doesn't go very far at all, and as you can see from here to here, right, it doesn't go that far at all. Then the one at the lowest nozzle is the strongest. And of course the one in the middle is the middle one, but all we're really fussed about is the weakest one and the strongest one. Now, why is there a difference between the two distances that the water nozzle travel? Well, that's all got to do with the fact that pressure at depth is really equal to the height of the column of liquid above the outlet. Okay, so that's a really fancy way of saying pressure is really determined by how much water there is above where you're actually trying to release the water. So, and that's represented by these H's here. So let's say H1, H2, and H3. So we can see above nozzle 1, actually let's do this in a different color now. Above nozzle 1, we have a height of a column of water of height H1, and above nozzle 3, we have a height of a column of water of H3. So we can see that there is a much bigger column of water above the third nozzle, meaning that there's more pressure coming out of the actual nozzle itself. So let's actually look at an equation to really sort of like solidify all of our understanding. So pressure is equal to H rho. I know it looks like a P, but it's a rho. They're really difficult to draw, but if you get the rest of the equation right, it will be okay. So pressure due to a column of liquid is is HP, sorry, rho, G. Okay, so G being gravitational field strength. So let's have a look at some of these units, right? So pressure here is again just normal pressure, so it's in pascals. H is the height of the column of liquid, which is in meters. P is the density of the liquid itself, so that is in kilograms per meter cubed. And G is just gravitational field strength, which on Earth and at sea level, right, is 9.8 kilograms. Sorry, not kilograms, newtons kilogram. Okay, so we have these three things, but what is this equation really showing us? So let's have an actual look at this one right now. We have here our column of liquid, so I'm going to draw that like this, okay? So that is our column of liquid of height H1. Now this is above our first nozzle, nozzle 1, so N1. Now I have another height of H2, sorry, this is H1. Then I have another height of H3 over nozzle 3 and 3. We can see that there is just more water above nozzle 3. If there is more water above nozzle 3, there is more mass, right? So there's more mass. Now, at the outlet of nozzle 3 right there, right? Pressure we know already is force per unit area. If we have a higher column of water, we have more mass. If we have more mass, mass multiplied by gravitational field strength is weight, and weight is a force, so we have more force due to the greater weight of water above the actual nozzle, and so we get a higher pressure coming out of the third nozzle. Now, if we get a higher pressure, the water comes out faster, so it goes further, and that really explains why if you have a higher column of water, we get a higher mass, and so we get a higher weight, and so we get a higher force, which means that our pressure at an outlet, right, so that would be these nozzles here, is greater. If our pressure is greater, our water or whatever liquid, right, comes out faster, and so it travels further. That's all there really is to pressure at a depth. Okay, so now let's have a look at this worked example. We're going to switch things up a bit, and we're going to be doing a 6 marker this time. So as always, we're going to go through it, and we're going to highlight all of our keywords. So in this question, you will be assessed, that just tells us that it's a 6 marker. Okay, so the information in this box is about the properties of solids and gases. All right, so solids have a fixed shape, and they are difficult to compress, to squash, right? So gases will spread and fill the entire container, and they're easier to compress, to squash. Use your knowledge of kinetic theory to explain the information given in the box. You should consider the spacing between particles, the movement of individual particles, and the forces of between the particles, right? So these 3 prompts here, so this one, this one, and this one, they actually give us exactly how we need to structure our answer. Now remember, this is a 6 marker, which means that we need to make 6 key points. Now we're looking at solids and gases here. So if we divide 6 by 3, sorry, if we divide 6 by 2, we get 3 points for each of them, and we have 3 points. So we're really looking at the spacing between particles, between solids and gases, the movement of individual particles in solids and gases, and the forces between particles in solids and gases. Right, so straight away, let's just draw a box here to represent the particles within both solids and gases. So I already have my gases pen, so let's do that first. Now we know that the gases, the particles are very spread out, right? And it actually tells us right here, the particles will spread and fill the entire container. So I have some spread out particles right here. Now, in my solids, however, I know that my particles are in a fixed lattice. If you remember that term, that means that they're in a fixed, neat rows, right? Like this. I need to draw much more, but I'll be here for ages if I do all that, so I'm just going to leave it like that. Okay, so now we have our two diagrams. Let's actually start writing our question itself. So, you wish to consider spacing between particles. So, in solids, the particles are very close together. So this means that they can't really get closer. So that means that compression, cannot be compressed. Compress as particles cannot move closer. Okay, so that's our first point there. Now let's do the same point, but for a gas. So we can say that in gases, particles are very spread out, so they can move closer, and so gases can be compressed. Okay, so that's 2 points right there. Now let's do 2 more points and have a look at the movement of individual particles. So I know that in solids, we just said that they're in a fixed lattice. So solid particles in fixed lattice. So this means they vibrate in place, right? Okay, so they just stand there and they sort of shake. But in a gas, the gas particles free to move. Now, how do they move? Do they move in a really ordered, structured way? No, they go all over the place. They move randomly. Move randomly. Okay, so that's our 4 marks right there. So let's do our final 2 points. Now, we want to know about the forces between the individual particles. Okay, so let's try and work this out just for my diagrams. I know that my particles in solids are stuck in place. Why would they be stuck in place? What's holding them there? Well, that would be the strong forces of attraction between the two particles. So, forces between particles in solids very strong. So because they're easy to because the forces between the particles are very strong, that means that the solid has a fixed shape. Okay, so now because we have made these 2 points right, so because remember our entire question is about explaining the information given in the box. So we're not just describing solids and particles, we're really looking at how their properties explain the information given here. Okay, so because the force between particles are very strong, the solids have a fixed shape. But now in gases, the forces between particles weak, and so particles spread through container. And that is all of our 6 marks secured right there. Now, as always, you can see in physics, if you work through logic step by step, a very hard question suddenly seems quite easy and straightforward. Okay, so now let's have a look at a harder example. As always, we're going to go through and we're going to highlight all of our keywords. So, a crate in a warehouse exerts a 10,000 Newton force on the floor. Alright, the base of the crate has dimensions of 0.5 meters by 3 meters. Now, calculate the pressure on the warehouse floor caused by the crate. Give your answer to 3 significant figures. Alright, so let's do that. First of all, let's write down our pressure equation. Pressure is equal to force over area. Now, force is already given to us, that's 10,000 newtons. Now, we want to work out area. So how will we do that? Well, we're given the dimensions, and so if we know dimension of a square is 0.5 by 3, work out area of a square, it's just length times by width. So we do 0.5 multiplied by 3, and that gives us 1.5 meters squared. That's our area. Remember, those are the units for area. Now, what we do now is input all of our numbers into our formula itself. So we do 10,000 over 1.5, and that gives us 6,666.67 newtons per meter squared, because remember, that's our unit. We can also give it in Pascal, either one is fine. Now, it says give it to 3 significant figures. Alright, so let's count 3. 1, 2, 3. there, right? So what we need to do is convert these final two into our significant figures. So we end up with 6,667 newtons. Sorry, no, not that. 6,670 newtons per meter squared. Sorry about that, but that's our answer right there, and that gives us 2 marks.